here just because it's good to get ready for next year. If you are planning on using anything for points in the grade book, we do need that by Friday. We're only going to meet up through Thursday. So whatever we assign on Thursday, we need it by Friday. So I know that's a quick turnaround. Hang on one sec. I got to stop the piano.
So while Mrs. Ballard is stopping the piano for my kiddos, I think I just posted the web assign from last Thursday, and I will fix all of them right now. They say that last Friday was the last day you could do them. I'll fix them so that they all say this Friday at 5.
Yep. I got you guys till 5 o'clock. So, so yes, please by 5 o'clock, because we do have to get our grades done and in, and we would like to just get that over with. And then anything by Friday is really what our big concern is this week. Okay. But we're going to learn some new stuff today, tomorrow, and the next day, and we'll put an assignment with it. So if you guys want to practice, you've got some practice. Okay. All right. We are going to, I'm going to share my screen.
Sounds good.
Okay. Here we go. I'm sharing. You should be, Miss Rondo, you seeing it?
It's loading, but yes, there we go.
Presenting. Okay. So, and you should be seeing my notebook now, right?
Yep. You are good to go.
Awesome. Okay. So we're going to talk about the fundamental identities, and we're doing this more out of just practice of seeing these more. The next 2 lessons, you kind of need to have seen a little bit more of this, just to have the practice and the exposure to it. Okay. I will try to see if I have these written. I think we wrote them out somewhere. So remember these from last week. Maybe you have them either written in the column, we rewrote them in the column, or we saw them, or they're back a few pages in your notes. We're going to be using these identities again. Okay.
Mrs. Ballard, can I interrupt you for a quick second? I'm sorry. Just want to remind everyone that those identities that Mrs. Ballard just showed are on the very first page of your notebook in the left-hand column. I don't know if we ever mentioned that, but that has a whole page of formulas. They're on left-hand column. It's about halfway down: reciprocal identities, quotient identities, Pythagorean identities. Anyways, they're all there. If you can't remember where they are, you can always flip to that page.
Yep. Thank you. That's a really good point. And when you're in our classrooms, you guys, even for next year, we have them posted. So if you need them, they're there. So I don't worry about you having them completely memorized. So, all right. So when I see something like this, I'm trying to simplify this expression as simple as I can get it. So I'm starting to replace it with with any of those list of identities. And we have one of the identities that's cosine squared plus sine squared. I'm not sure if I'm doing it in the right order, equals 1. Now, if we were in my class or in our classrooms, we would have a sign up there that we would see this popping out, but we're not there, unfortunately. So I'm going to solve this equation. This is one of my Pythagorean identities, and I'm going to move this to the other side. So I know that cosine squared equals 1 minus sine squared, and I know I've lost my variables. I shouldn't have done that. But see how this is equivalent to that? So I'm allowed to replace it with cosine squared. So I'm dropping secant squared x. I'm going to replace this with cosine squared x. Now I'm going to see if I can still get simpler than that. So another name for secant squared, I'm going to use one of the reciprocal identities, is 1 over cosine. And if it's whatever exponent I have, I use that exponent. So cosine squared. And now you'll notice I've got cosine squared divided by cosine squared, which we know is just equal to 1. So that's kind of our best case scenario. Get it down to 1, it all goes away. All right. Looking at example 13, I'm going to do the best I can to squish it in there. So now we're in the, what did I do? This is an old one. Okay, we are factoring. Awesome. I had another one in there that apparently 2 years ago, and I took it out. Nice. Okay, this one here, I have to, I'm supposed to factor. And let's just remember when we had something like 2x squared plus 4. First thing we always look for when we're factoring is the greatest common factor. So we would pull out a 2. Well, you're going to see that factoring happen in lots of different weird algebraic places the more and more we go up the food chain here in calculus, okay? So you'll notice that I have a secant squared in both of those, so I'm going to pull my secant squared out. and I have left behind a tangent squared x, and then remember there's always a coefficient of 1, so plus 1. This looks awfully Pythagorean to me. I'm going to go scroll back up to my Pythagorean identities here just to check. I have 1 plus tangent squared, and sure enough, it's right there. It's equivalent to secant squared. So I'm going to substitute secant squared in for that one. So I've got secant squared x times secant squared x. Well, secant squared x times secant squared x would be secant to the 4th x. Anything I can do with a polynomial or an algebraic expression, I can also do that same thing with trig. How are we doing, Ms. Rondo?
We're doing good.
Okay. All right. So the next one, I'm going to change it up a little bit. We are going to factor it. I'm going to change it for a minute. I'm going to go back to the factoring that we're used to. So I'm going to look at this as 1 minus 2x squared plus x to the 4th. Okay, so all I did was I took out the signs and I plopped x's in there. When we see something that's a trinomial, well, we know when we factor a trinomial, we do a magic x. You do the magic x too, right, Ms. Rondo?
Yes, I do.
Yeah. And so we multiply the first and the third together. So that's 1. And I know this is a little bit looking backwards because we typically like the x up front, but that's okay. We can do it this way. And then the bottom is -2. So I need 2 numbers that multiply to 1 and add to -2. So I would say that that would be -1 and -1. The little bit of a catch on this one is that okay. This one's a little bit weird because of the way it's written. Yeah.
This is why you're doing this one.
Thanks. Okay. So this negative is actually going to be for the back term. Okay. When I take apart that 1, it's always ever going to just be 1 and 1. And this back term is going to make it negative. And then whatever goes in here, I don't know if you've ever noticed this, it's always what's in the middle. So we're going to throw whatever's in the middle in there. Okay. So that's the exact same thing as the way that this one would factor. Just instead of putting x's in there, we're going to put signs in there. So 1 minus, let me do that a little bit better. 1 minus sine squared x times 1 minus sine squared x. It actually ended up being like a perfect square trinomial. I could be super cool though the way I write that, because you want to be super cool. Yes, I am, because I can write it squared. And then I know this, we did that one example ago, didn't we? 1 minus sine squared, isn't that cosine squared? So I could substitute the cosine squared in there. So cosine squared x squared. And when I square a squared, I get cosine to the 4th x. I didn't necessarily have to do this step. I could have done cosine squared times cosine squared, and I would have gotten to the exact same spot. All right, how are we doing? Any questions, concerns?
I would just say to add to it what Mrs. Ballard did with her factoring. It looks weird because the x is in the last term rather than the first term. If you wrote it in descending order and factored it, it would probably be a little bit more what you're used to.
Yeah, and it'd probably come out to be the same thing.
It
maybe
would.
I don't know.
It would look a little different, but it would still give you the same end result.
Yeah. All right, I'm going to keep going. So we've done a greatest common factor. We've done a magic x. Luckily, didn't have to do the box. And then now we've got a squared term times a squared term and a squared term. So that means I have a difference of squares factoring. That's one of our favorites. So yes, I know
it's going to come up in the next couple examples. So.
Oh, great. My example numbering is kind of weird here. I'm noticing a 16, then it skips to 19. I wonder what happened.
Mrs. Ballard can't count.
Notebook? Ms. Rondo, is that the way it's in the actual notebook?
Yes, it is. That's what I tell my students all the time. When the numbering's off, I just tell them that Mrs. Ballard can't count.
That's right. I can't. Nope. Can't count. Okay. So I'm taking the square root of both sides here for differences, or both terms for a difference of squares. So square root of the first term would be secant squared x, and that goes in the front of both of them. Square root of the last one would be tangent squared x. And then difference of squares, I make one a plus and I make one a minus. All right, so from here, I need to see if I can figure out how to simplify that. So I'm going to go up and I'm going to look at these are all squared things. I know it's got to do something with Pythagorean. I know I'm doing a lot of scrolling today, but I'm going to scroll up and refresh my memory on this one here again. So 1 plus tangent squared equals secant squared. Okay, I'm going to write that down back here. 1 plus tangent squared equals secant squared. Obviously, I'm abbreviating. I don't have that exactly, so I'm going to play with this a little bit. I'm going to try to move that tangent to the other side because it looks like my tangents and my secants are on the same side of the equation. So secant squared minus tangent squared equals 1. Notice it's the same thing as I have here. I know, super exciting. So I can replace this with a 1. And then I'm just going to drop this down the way it looks. Secant squared x plus tangent squared x. And I think that's it. So we're good to go. That's as simple as that one got. I mean, guess you could write it without the 1 on there. Secant squared x plus tangent squared x. My squared's in kind of the wrong spot. But you get the idea. All right. Looking at the one that says example 16, I am going to do good. Oh, actually, let's see what they think we should do.
Oh,
we put it in the chat.
Yes.
We've got a binomial times a binomial. What do you guys think we should do? Any ideas, Miss Rondo?
Not yet. Give him a minute. It's not Monday, but it's kind of like Monday.
I know it is kind of like Monday.
Oh, I got a question mark and not a question mark, a foil.
Ooh, they know
like
what they're doing. I do like that. Foil is exactly what we're supposed to do. So see, you guys, it's not a big deal that we all of a sudden took variables and we threw some trig in there. The algebraic operations are the algebraic operations. You do them the same way, or no matter what's in there. So,
Mrs. Ballard, can I ask an additional question? Or to the class to put in the chat?
yes.
Is there a way we could do this without foiling by using maybe one of our special properties of factoring? Let's see if anyone can come up with that. Foiling is correct. We foil, but there is what we call a shortcut.
Oh,
know what that is?
Oh, I'm seeing it now. It's interesting that we have a tangent plus a secant and then a tangent minus a secant.
We'll see. Give him a couple more seconds.
I think that might have a fancy name.
All right, looks like we're not quite sure, but that's okay. I'm super thrilled that we got foil, so we can do foil.
Me too. Okay, so it's going to come up here. Okay, what Mr. Rondo was asking. All right, so I see tangent times tangent, and that would be tangent squared x. Then we've got tangent times negative secant, which would be tangent x secant, or negative secant x. And then secant times tangent, I'm going to write it with the tangent first since that's how I started the other one, tangent x, secant x. And then I've got secant times negative secant would be negative secant squared x. Now, what Mr. Rondo was referring to is when we have these two things that are exactly the same, but with the negative in the middle, we call those conjugates. I think I'm spelling that right. And remember, that means that we skip the O and the I, and we don't have to write that part down. So really, we could have taken the shortcut if we had recognized it. Since you didn't, I didn't take the shortcut. But
difference of squares.
And it becomes the difference of squares. Isn't that amazing?
And this actually, to totally interrupt you, Mrs. Ballard, I'm so sorry, but this right here, guys, in just a couple minutes when I jump in and do example 20, I'm going to skip this part because it's exactly the same that what you just did with Mrs. Ballard. So that multiplying the conjugates together gives you difference of squares. That was like perfect, Mrs. Ballard. This lesson is amazing.
I know. It's like we planned it. All right. So we have Pythagorean probably going on again. So I'm going to check this guy out. We just wrote it down right here that we know that secant squared, this was our secant squared, equals 1 plus tangent squared. So I'm going to replace with that. I could replace the tangent one. It doesn't really matter. You're going to get the same answer in the end probably. So I'm putting in the 1 plus tangent squared x. I'm going to distribute that negative through. So tangent squared x minus 1 minus tangent squared x. And really be careful on these because I can see myself right here almost looking, that looks like a 2x. You've really got to make sure that your squared is apparently an exponent on your trig there. And then you'll notice that the tangents cancel, and we're just left with -1. Are we good, Mr. Rondo?
Yes, we are good.
Okay, I got one more here that I get to do, it looks like. I'm going to do my work here off to the side, so I'm going to move this one kind of over here. And this one, again, this one's kind of weird because we've all of a sudden got rational and irrational expression here. I know the only way that I can add rationals together is by getting a common denominator. So I'm not going to write out everything, but I know that my common denominator has to be these guys multiplied together because there's no way there's common factors or anything goofy in there. So I'm just going to use them both. Now, we had done rational expressions, but it's been a long time, okay? When we do rational expressions, to get your common denominator, you want to multiply by what's missing. If you were in my class, this is when we did the circling the red and the blue stuff, okay? So I noticed that I have secant plus 1, and I have one of those there, which means I need to multiply by the other one. I'm going to multiply by secant x minus 1, and I'm going to distribute that 1 through, so that gives me secant x minus 1. Then I notice, let me see a different color. I have for this one, I match the secant x minus 1. I'm missing what I highlighted in yellow, so I'm going to multiply by that. So I'm multiplying by secant x plus 1. I'm distributing not just a 1, but a -1 this time. So negative secant x minus 1. Andy, do you have a joke?
Yeah.
All right. And then you'll notice that this and this are the same, but opposite signs, so they cancel. And we've got -1 and -1 is -2. My denominator I can FOIL out, and I'm going to skip. I noticed they're conjugates, so hopefully you did too. So I'm going to skip O and I. I'm just going to go to F and L. So secant x times secant x is secant squared x, and 1 times -1 is -1. And again, that looks awfully Pythagorean to me. It looks like it's playing off of this one here. I need us to find secant squared minus 1. So I'm going to rewrite a little bit. I know I have 1 plus tangent squared. Yes. Equals secant squared. So I'm going to try moving the 1 to the other side. So I have tangent squared equals secant squared minus 1. So I know I can replace this with tangent squared. And then typically with trig, we don't like seeing denominators. So I use a reciprocal identity, and the reciprocal of tangent is cotangent. So it'd be -2 cotangent squared x. And that's kind of the fun thing about trig is it's like this big puzzle that you have to put together, and you got to kind of keep simplifying and keep simplifying and keep simplifying. All right, Andy, come tell your joke. Got to have our joke of the day. I know you went a whole long weekend, like a 4-day weekend for us even.
Right. Long weekend.
So it was a long weekend, and we've only got like 3 jokes left until what we're going to call the end of the school year for us here. All right, Andy, tell us the joke.
What do you call a rodent with babies?
I don't know. What do you call a rodent with babies?
A quadratic parent.
Oh, with 4 babies, maybe?
With babies.
With babies, a quadratic parent. Maybe it was with 4 babies.
Quadratic.
Oh, a rat with babies?
I don't know.
Was that, a rodent with babies? Oh, I get it. A quadratic parent. That was a good one. You got another one? Your bonus joke, guys.
Okay, bonus joke.
What does a fisherman use to make sure he has the right fish to make a profit?
What does a fisherman use to make sure he has the right fish to make a profit?
Yeah.
I don't know what.
A quadratic inequality.
Okay.
He's getting some good ones. I'm not sure he understands the math. He's found some good jokes. All right,
That's some
go work on your homework.
quadratics going on.
Yes, we do have a lot of quadratics going on. All right, Mr. Rondo, you are up.
Okay, let's see how I don't really look at the examples ahead of time, so we'll see how I do.
I'm sure you'll be fine.
Oh, I did not share my screen. That's a problem. Let me
Yes, we
actually
have
share
not done that yet.
You guys can't see what I see? No. Let's fix that. Okay, Mrs. Ballard, keep me on point there. Can you guys see it?
It's starting to come.
Okay.
There we go. We can see you.
All right, so we are on example 20. This one is it flows really nicely from the last two that Mrs. Ballard did. Rewrite the expression so that it is not in fractional form. So we're trying to get rid of the fraction. When I look at this, I see that tangent and secant popping up again. This is kind of not an obvious skill here in this problem. It's one that takes practice to see and kind of use, and it's actually one that you use in calculus sometimes to rewrite things in different ways. So we want it to not be a fraction, but I'm going to work with it for the moment in fractional form. I want tangent and secant to go away, but just tangent plus secant doesn't do me a whole lot of good. So I'm going to use a skill that's called multiplying by the conjugate. We use it kind of with our radicals when we rationalize. It's the same idea. So I'm going to multiply by the conjugate on the top and the bottom. So I'm going to say tangent x minus secant x. That's the conjugate because it's the same expression, only minus secant x instead of plus secant x. And I have to do it to the numerator and denominator to make sure that I am multiplying the fraction equally there. So I'm multiplying by 1 because anything over itself is 1. All right, so then when I multiply that through, I'm going to distribute on the top. I'm going to just go ahead and actually distribute the 5 through this, kind of as if there were imaginary parentheses here. So I get 5 tangent x minus 5 secant x. Fantastic. And then on the bottom, we're going to use what we saw with Mrs. Ballard. When I'm multiplying my conjugates, I basically am doing difference of squares where I take the first term, or just as she said, do the F and the L. You skip the O and the I for FOIL. I'm not a big FOIL person, but it does work that way. So I'm going to take tangent times tangent is tangent squared. And then secant times secant, or secant times negative secant, is going to be negative secant squared. So there's my difference of squares, and you guys already saw that kind of worked out for you. Then I see that squared business. When I have squared secants and tangents, I'm going to look at my Pythagorean identity stuff, and I'm going to do it just slightly differently than what you saw with Mrs. Ballard, but it's the same identity. The 1 plus tangent squared equals secant squared. That's the Pythagorean identity that we're stealing from. I'm going to take this and I'm going to see if I can make it look like tangent squared minus secant squared. So I want it to say tangent minus secant. So I'm going to subtract from the identity. I'm just going to play with this a little bit, move things around so I can make it match, if I can. So I'm going to subtract secant squared from both sides. So I have 1 plus tangent squared minus secant squared equals now 0. So I have tangent minus secant, yay, or tangent squared minus secant squared, but I don't want the 1. So I'm going to move the 1 to the other side. And I get tangent squared x minus secant squared x equals -1. Awesome. So now that I have this, I'm going to replace, instead of tangent squared minus secant squared, I'm going to replace it with -1. So I have 5 tangent x minus 5 secant x all over -1. My goal here was to rewrite the expression so that it's not a fraction. So I'm going to divide each part of that expression by -1. So I get -5 tangent x plus -5 divided by -1. It's positive. So plus 5 secant x. And at that point, I have achieved my goal. I no longer have a fraction. I could possibly continue further and play with the secant, because secant we know is 1 over cosine, and do some stuff there, but I don't know that I'm super interested in that. Mrs. Ballard, do you want me to go further, or is that sufficient for you?
No, I think you're sufficient. The only thing that I don't know how how far WebAssign is going to take the answer, because that would be where it would be. Is there something else that we could maybe factor out of there?
We could factor out, pull the 5 back out. So at the top,
Yeah.
when I said I was going to distribute that 5, it is possible you wouldn't do that, or you could come at the end and pull that 5 back out, or even pull out -5. It's again, not knowing how WebAssign would do it. Personally, I like my numbers to be, my first number to be positive. So I would probably pull out -5 and say it's tangent x minus secant x. But that's, you know, depending on how it wants to write it. You could also write it as 5 negative tangent x plus secant x if you just factored out a 5.
Yeah.
And
totally agreed. Totally
What's that?
agreed. The only thing that I would do, like the only slight difference I would do is sometimes in calculus, it helps us if we don't don't distribute too fast. And this would have been a good example of that, where we maybe don't distribute that 5 in right at the beginning and we just carry it to the end and put everything in parentheses. Totally. And I don't know what WebAssign is going to do either. So.
Right. And that it totally depends on the problem. And what you're trying to accomplish. So with this one, without knowing exactly what, you know, other than not writing it as a fraction, like we wrote it not as a fraction, is that what we're looking for? It depends on our overall purpose, for sure.
Yep.
Like I said, we could
manipulate it just a little bit more to get it to where it needs to be.
Yeah, we could even, if I wanted to keep going further, I could change secant into 1 over cosine x. And then I could change tangent into sine x over cosine x and see how those have a common denominator. So there's even more work I could do. But for now, that's probably enough. So it just depends on what you're looking for.
Yep.
For sure. I'm going to get rid of that guy. All right, so let's continue on. Actually, before I do that, just a quick shout out. Are there any questions? And that one kind of went a little crazy at the end.
No questions. They're super quiet.
Okay. All right, so on to 21, use trigonometric substitution to write the algebraic expression as the trig function of theta. And they tell us that theta is between 0 and pi over 2. Just a reminder that that's like saying 0 degrees and 90 degrees. So we're talking about an acute angle in quadrant 1. All right, basically, I'm literally going to do substitution. That's what it says. So I have square root of 4 plus 2 tangent theta squared. So I replaced my x with 2 tangent theta. Then I'm going to square that. So remember, when I square that, I'm going to be squaring. The squared goes to the 2, and it's going to go to the tangent. So I'm going to say plus 4 tangent squared theta. It does not go to the theta. Remember, that's because when you do tangent theta squared, that's what we're really doing. We write it with the squared next to the tangent to let us know that the function is squared rather than the angle. So the angle is going to stay the same. Just be careful there. Okay, so once I have that, then I see those matching 4s. So I'm going to actually do a little bit of factoring here. I'm going to factor out 4. When I pull out a 4, that will leave me with 1 plus tangent squared theta. Then I'm actually going to look at that. I see 1 plus tangent squared. That should look somewhat familiar. We've been working with this fabulous Pythagorean identity that says 1 plus tangent squared equals secant squared. So I'm going to replace this whole thing with secant squared. And then I'm looking to take the square roots. Remember, this is multiplication, so I can deal with them together. I can take the square root of the separate parts and then pull them out. So the square root of 4 would be 2. The square root of secant squared would just be secant. And there we go.
That is awesome.
Yep.
Go ahead.
Oh, I was say that one's not, I mean, there's trig in it, but this is, again, what Mrs. Ballard said before. There's trig in it, but it's really just the algebraic practice with seeing that trig involved. It's not,
yep.
not too crazy.
I totally agree, Miss Rondeau.
Sounds good. All right, let's look at 22. Same kind of thing. I'm going to follow the same basic setup here. I'm going to say 64 minus 16, and I'm going to replace x with what I'm told x equals. So 2 cosine theta, and I'm going to square that. All right, so then I have 64 minus, now the 16 is not part of that squared, so it's going to be minus 16. When I square 2 cosine theta, the 2 gets squared, it becomes 4. And then cosine squared, and remember theta does not change. All right, so then I have a little bit of multiplying. 16 times 4 cosine theta, that's going to be 64 cosine squared theta. And you'll notice a very similar thing to what we saw a moment ago. I see matching 64s. I'm going to factor it out. So I have 1 minus cosine squared. And this definitely, even the last one, it would be really handy to be in our classrooms where we could see this. But when you see those squared trig functions, that's your hint that it's a Pythagorean. This would be our cosine squared plus sine squared equals 1. Or if you remember the pickup line, I wish you were cosine squared and I was sine squared. So together we could be 1. There you go.
Miss Rondeau's telling jokes now.
We did that one a while ago, but just in way to remember this one.
Yes.
But if we were in our classrooms, we not only, this is the main identity, but we would also see different versions of it where if we solve it for cosine, we would subtract or move the sine squared to the other side. So we would see one that looks like this. 1 minus sine squared. We would also see the reverse. We basically have these all listed out. And because we're not in our classrooms, you guys don't see those regularly. So we would also have the version where we solve it for sine squared. So we'd move the cosine over. So we'd get sine squared equals 1 minus cosine. So you can see those are the same identity. They're just written in different forms. This one is the one that's going to help me out because it says 1 minus cosine. So I'm going to replace it with sine squared. So I have 64 times sine squared theta. And then once again, taking that square root, the square root of 64 is 8. Square root of sine squared is going to be sine. Fantastic. And we have one more example to go. All right, so example 23, rewrite the expression as a single logarithm and simplify the result. Hopefully you haven't forgotten about logs. Remember, ln means natural log.
Ooh, this is like my favorite problem.
Is it?
Yeah, it's like one of my favorites.
All right, so we have natural logs, and works just like logs. We get to see that we have matching, since they're both natural logs, they have matching bases. And we have addition. Oh, I'm going to ask a question for our chat. When we're dealing with logs, what does addition turn into?
Oh, we should know that. We spent a long time on logs this year.
Yes, we did. What can I change addition into?
Oh, multiplication, Casey says.
Multiplication sounds wonderful. Multiplication. So I'm going to condense this or squish it together into a single log, natural log, and I'm going to multiply, just with brackets, I guess. I have cosecant theta times tangent theta. And with this, the absolute values are just basically to say we want a positive answer. So I'm going to ignore those for a moment and just look at cosecant times tangent. Keeping in mind that I do want only the positive result here. Just for a minute. All right, so then cosecant I could rewrite as 1 over sine. And tangent I could rewrite as sine over cosine. And when I do that, the sines cancel out and I have left 1 over cosine. So I would have 1 over cosine. I'm writing a lot of steps here because I don't want to lose anyone. And I haven't forgotten that these are all, we want just the positive result, the absolute value. So I have natural log. I'm going to rewrite 1 over cosine as secant, my little absolute value. So now I'm down to natural log. That's really squished over, sorry, or pushed over. Okay, and then I'm going to remind us of something that is not a thing that we use a ton, but we did use it before, are even and odd functions. And basically was saying that if I have cosine of negative x, that's the same as cosine of x. And it also applied to secant. If I have secant of negative x, it's the same as secant of x. So basically, if I put in a positive angle or a negative angle, the result for cosine and secant is the same. So with that, as long as, well, I'll probably just leave it there. Sorry, I was going in different directions. But my angles, then it doesn't matter if it's positive or negative, that I'm going to get the same result, but I still want an overall positive answer. So I think I'm going to leave those absolute value bars there and call that good. Mrs. Ballard, any comments?
No, I'm so jealous that you got to do my favorite problem.
I'm sorry.
I love seeing logs and trig together. It's amazing.
Well, this would be like, this one we should definitely maybe add for the future. When we get to do the power rule with logs, that's like my favorite. For your students, they don't get the joy of hearing me say it, but my students, they know that it's very exciting when we get to do the power rule. In fact, they're probably going, what is she talking about? Because I never call it the power rule.
Awesome. Well,
yes.
The nice thing about being virtual is we get to say goodbye because and let you out like 20 minutes early of class.
Yes. Let me get rid of this so you guys aren't stuck watching my screen. I'm so sorry.
Yep. So we will see you guys on tomorrow, and we will probably put an assignment up here in just a little while, okay? So we'll see you guys later. Bye.
Thank you guys for coming. Early day. Bye.
Awesome.
Awesome.
Easy
Don't forget
today.
to stop recording.
Oh, yes. Thank you. Let me hit that button real quick before you go anywhere because it's quicker that way than